In this video, we'll be covering the topic of acid-base titration. This is normally a topic I would spend probably about a week to a week and a half of in class, but I will give you the short, condensed version of it for this video. You guys are going to need a notebook, you're going to need something to write with, and towards the end, a calculator may be a little bit helpful as we are going to be doing a little bit of math. Once you have all those things ready, you can pick the video back up. Okay, so we should probably start off by explaining what a titration is. A lot of times when you're in a lab, one of the tasks that you're going to have to do is you're going to have to make reagents or chemicals that are involved in a reaction, and they have to be made to a certain concentration. In order to determine the actual concentration of the solution you created, you have to perform what's called a titration. Now, the math that we did a couple of weeks ago, where it was moles divided by liters, that will give you a very good approximation. However, remember, when you scoop things up and put them into containers, you're going to lose some substances. For example, sodium hydroxide, when you make a solution, even though it may say half a gram, that's not just of sodium hydroxide, it also absorbs a lot of water. So you'll probably have like 0.35 grams of sodium hydroxide, and the other 0.15 will be water. So what we need to do is we need to determine the actual concentration of the solutions before we go doing reactions with it. And the way that we do this is basically a stoichiometry method. We take our unknown concentration solution and we react it with a solution that has a known concentration. And if we measure the exact volumes of the unknown solution and the known solution required to get it to react precisely, we can figure out the concentration involved. Right, so this is a titration. Typically what you would see when you're doing a titration is you would have a flask sitting on a countertop with a liquid in it, and then you'd have this long glass tube with a little dropper at the end called a burette, and you would one drop at a time add a solution from the burette into the flask and wait for the reaction to finish. Right, and you knew exactly how much of the solution you put in the flask. You can measure with a burette, like a graduated cylinder, exactly how much of the solution you added, and from there you can determine the concentration. If you want a relatively easy way at home to kind of visualize this, take some baking soda, dissolve it in water, and then just drop by drop by drop, start adding some vinegar into that. Right? You'll know the reaction's happening because the reaction of vinegar and baking soda produces CO2 gas or bubbles. You just keep adding that vinegar one drop at a time until the bubbling stops. When the bubbling stops, you've reacted exactly all of the baking soda, so there's no need to add more vinegar. And from the volumes of everything involved, you can figure out how concentrated your baking soda solution is. Right, so that's kind of the idea behind what we're getting at here. Now, we won't always be titrating things that produce gases and bubble and all that. A lot of our titrations are actually acid-base titrations. They don't produce gases. The only two products they would produce are water and some type of ionic salt. So we have to have a way to easily determine when we're done. Now, the point at which the reaction is finished is called equivalence. It's called equivalence because at that point, you have an equal number of moles of acid and an equal number of moles of base in your flask. So you have what's called neutralized the solution. Neutralized doesn't necessarily mean pH of 7. Neutralized just means that you've reacted exactly all of the acid and base in that mixture. Right, and the way that we determine equivalence points, there are a couple of different ways you can go about this. The most common way is to use what's called an indicator. An indicator is a solution that changes color when you get to the equivalence point. So when the reaction is complete, you get a color change. A very common indicator for a type of reaction called redox is starch. Right? Any redox reaction involving an iodine compound We typically use potato starch for this because when the reaction is done, when most iodine redox reactions are finished, you produce diatomic iodine, I2. I2 reacts with potato starch to turn that dark blue complex that you see whenever you put iodine on a potato. Right, so one of the reasons why this is a really good indicator is up until you get to that exact moment where the reaction is done, the solution is clear. The potato starch is colorless. It may turn a little bit milky white, but mostly colorless. And then the instant you hit equivalence and you produce that first molecule of I2, the solution turns like midnight blue. So it's clear, 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 blue. Right, that's one of the things we're looking for in a good indicator, is a very rapid color change from one thing that's easy to see to another thing that's easy to see. Acid-base indicators are no different. Now, the way that an acid-base indicator works is that an acid-base indicator changes color based on the pH. Right, so different colors at different pHs. A couple of common indicators that you're familiar with are litmus and red cabbage juice. In acidic solution, both of those indicators are red. In basic solution, they're blue. In a solution around pH 7, they're kind of purplish. An easy mnemonic that you can use to remember litmus is blue to red acid. Right, so it goes red into purple into blue, going from acid to base. In the lab, our most common indicator is something called phenolphthalein. We also just call it pheno, P-H-E-N-O, as an abbreviation because, we're lazy. We don't want to write out the whole word. Up until you hit a pH of about 9, phenolphthalein is completely and perfectly clear. Once you hit 9, it turns pink. It looks kind of like red wine, or maybe a very diluted like cherry or strawberry Kool-Aid kind of color. Right, so it's clear, 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 pink. Right, so that's one of the reasons why we like using phenolphthalein. We use it over indicators like litmus or cabbage juice because of that very distinct change in color. Now, what we want to do is we want to pick an indicator. There are a bunch of different indicators you can use. We want to pick one that will change color at a pH really close to where we think it's going to end up at the end of the reaction. Now, we can actually approximate this. Again, if we were working on this in class, I'd give you like a bunch of things where we'd say, here's the acid, here's the base. Where is it going to be at equivalence? The short version of this is you want to default to whichever one is stronger. Right? So in case of a strong acid and a strong base, if they're both equal, they cancel out. So the pH at equivalence will be roughly about 7. If we're working with, say, a strong acid and a weak base, the acid is stronger, therefore the pH at the end will be a little bit more on the acidic side, so less than 7. Similarly, if we had a weak acid with a strong base, like vinegar and sodium hydroxide, that reaction, the base is stronger, so that wins. The pH at the end will be a little bit over 7. Right, so for other combinations, whichever one is stronger tells you which side to default to. And you don't have to get exact numbers when you're doing this sort of thing, because these pH colors work in ranges. So as long as you're within that range, you're good. Now, this graph right here is what's called a titration curve. This is another way that you can measure, that you can do titrations, is instead of using an indicator, you use a pH probe. And what you do is you have a special device called a drop counter, and as you add your sodium hydroxide, in this case, as you add that base in, each drop gets measured by that counter and added onto the volume and graphed. And every time it adds a drop, it takes the pH and it makes a point, and it just connects all those points to form a graph. This takes a lot more. This is actually a lot faster than doing it with the burette, the actual titration, but it takes a lot longer to set up and requires expensive equipment. Now, what a couple of things I want you to pay attention to with this graph. So first thing we're going to pay attention to is if you look at the starting pHs, there are actually two titrations on this same graph to kind of show you the difference. The lower one, the orange one, is hydrochloric acid. So this is a strong acid. Notice the strong acid starts with a very low pH of about 1. The weak acid, the purple one, which is so CH3COOH is acetic acid, otherwise known as vinegar, right? So this is a vinegar titration. Vinegar solution starts with a much higher pH, typically around 2 to 3 to 3.5, somewhere around there. And as we add the base they're adding is sodium hydroxide, same concentration to both. So as you add the base, the pH will gradually increase, and it'll increase slowly and slowly and slowly until you get close to the equivalence point. This is one of the great things about logarithm-based numbers is once you get close to a certain tipping point, it becomes very obvious the change is taking place. Right? So once we get close to equivalence, it actually labeled the equivalence points for these. They're both at 25 milliliters. But as we get close to 25, notice how the graph goes from really low to really high, and it only gained maybe a milliliter at most, right? So the first 24 milliliters, the pH went up by 2 units. The next 2 milliliters, it went up by 8. That's one of the key defining things about a titration curve. And to find equivalence, you just basically find the midpoint of where that rise happens, which in this case would be kind of right here at around 7. Right, so you can notice that there. The other thing to notice, this actually shows us the different things. Hydrochloric acid and sodium hydroxide is a strong acid, strong base. So equivalence happens at 7. Vinegar is a weak acid. Since the acid is weaker, the titration, the pH occurs a little bit above 7, actually at about 8.72. You're never going to have to calculate the exact pH of equivalence, so don't worry about it. Now, we can look at these diagrams, and by looking at the indicator ranges, it would seem that for the vinegar titration, phenolphthalein is the best indicator to use because its equivalence point is right inside that range. And we actually do use phenolphthalein for this titration. The strong-strong combination, it seems as though litmus would be the best indicator. However, remember what I told you about litmus a few minutes ago. Litmus starts off as red, and then it gradually becomes purple, and then gradually goes into blue. With something like litmus, it's really hard to tell when the reaction is exactly completed. So what we instead do is we actually use phenolphthalein. And you're probably sitting there thinking, but why? If it's at 7 and phenolphthalein doesn't change until 9, won't we be like really off? Well, here's the key thing. Here's the reason why we can get away with this. The difference in volume between pH of 7 on the strong acid strong base and pH of 9 on the strong acid strong base is maybe a drop and a half at the most. Right, so it's not a very large difference in volume, just a few hundredths of a milliliter. The difference in volume is so small that it's actually not going to be affected by significant figures. That's one of the reasons why we can get away with it. As long as you stop it precisely when you see that pink color and not a drop later, you can actually still get data that's just as good. Right? And it's a lot easier to go clear, 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 pink than it is to go red, 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 kind of purple, kind of purple, kind of purple, kind of blue. Right? So that's working with equivalence points. Primarily, what you're more interested in from a graph like this is you're more interested in the equivalence volume, which is where that dot is, so the volume of that dot. And we're going to use that when it comes to doing our math. Now, the math is actually very straightforward. It's an equation you've seen before. Right, so the titration math is based on an equation that we've used a few times before. I've shown you P1V1 equals P2V2. I've thrilled you with M1V1 equals M2V2. And now we're going to absolutely floor you with MAVA equals MBVB, where A is the acid and B is the base. Same exact equation. One caveat is that this equation only works if the ratio for the acid and base in your equation is 1 to 1. If it's not 1 to 1, you have to do actual stoichiometry out. Now, for the sake of simplicity, given the situation that's going on this year and distance learning and all of that, I'm going to make it easier on you guys. All of our titrations will be 1 to 1, so this equation will always work. If we were in class, I would actually have you do some out that weren't quite 1 to 1. Right, so again, same equation, same math, plug in, get your answer. Now, one thing I will be doing on these couple of upcoming practice problems is I will be using liters instead of milliliters, just to kind of keep your mind on the molarity is moles per liter thing. Right, because a lot of people tend to mess that part up. And I noticed that a little bit with the ideal gas law too. Some people are messing up liters versus milliliters on the ideal gas law. So we're going to be a little bit more consistent. So here's our first question, our first titration. We are reacting an unknown nitric acid solution with a known sodium hydroxide solution. First thing we always do is we come in and we label our variables. Sodium hydroxide, since it has hydroxide, is our base. So 0.180 is molarity of the base. 42 is volume of the base, 42 milliliters. Now again, I'm going to convert this to liters to be 0.042 liter. Right, just to be kind of consistent. Nitric acid is our acid. And we have the volume of the acid at 26. So volume of acid, 0.026 liters. All right, so now what we're going to do is we're going to plug this into our equation. MAVA equals MBVB. Right, so MA we don't know. VA is 0.026 liter equals molarity of the base, 0.18 molar. Now I'm going to leave out a lot of the zeros here to make my writing a little bit quicker, but we can just mentally put those back in when we do sig figs. And our volume of the base is 0.042 liters. So now all we do is we solve for molarity of the acid. That's just some basic algebra. And we get a molarity of the acid equal to 0.291 molar. Right, I get 3 sig figs here because 3 for the 42, 3 for the 0.180, and 3 for the 26. And again, this number should kind of make sense. It takes less acid to react than we had base. That means that if it takes less acid, the acid has to be more concentrated. Right, so we should get a higher concentration than we had for the base. So that's our first one. Our second one's going to work very similar. What I want you guys to do is pause the video and try to get me an answer to this. And once you have your solution, pick the video back up and I will go over it. Okay, so again, HCl, hydrochloric acid, is our acid. This is our molarity of the acid. Right, ammonia is a base. 0.8 is our molarity of the base. 10 milliliters is our volume of base, which is 0.01 liters. Again, we'll leave sig figs to later. We plug into our equation. MA is 0.0933 molar. Volume of acid, we don't know. Molarity of base is 0.8 molar. Volume of base is 0.01 liters. We solve for volume of acid, and we get a volume of 0.0857 liters, or 85.7 milliliters. And again, this number should make reasonable sense. The hydrochloric acid is much less concentrated than the ammonia, so it should take us a lot more of it to get the same number of moles. Right, so this is how the math is going to work. As always, if you have any questions, feel free to email me. Your assignment this week will be posted with the video. Your assignment next week will be an acid-base test. And then after that assignment, we're going to get into doing what's going to be one of the hardest things to do through distance learning, which is molecular structure. All right, so hopefully I will get all of your assignments sometime next week.